Hello and welcome, class, to another lecture where here we will be finishing up Chapter 7 with a discussion of one last bonding theory known as molecular orbital theory. So, without giving too much of a preface, since we have a lot to talk about, let's just jump into it by explaining how it's different and why it's necessary in addition to valence bond theory. Alright, so as we've discussed already, the premise of bonding is that chemical bonds will occur as atomic orbitals begin to overlap. So we introduced valence bond theory last time as a way to describe the molecular geometries that we see, that we observe when studying these molecules. That an s orbital, like carbon's 2s orbital, as well as its 3 2p orbitals, need to find a way to come together to minimize repulsion, maximize attraction, create some sp3 hybridized orbitals with the proper geometry that we see when actually observing a molecule like CH4. It turns out that valence bond theory can't take into account certain observable phenomenon. It's really good at being able to explain where the geometries of these molecules come from, but it kind of lacks in other areas. So here's an issue with the valence bond theory. Neither Lewis structures nor the molecular geometries predicted by valence bond theory can explain certain observable phenomenon consistently for all molecules. The big one that we are going to touch on today is magnetism. There are some molecules, some species that are magnetic that valence bond theory or Lewis structures cannot take into account, like how they're magnetic or why they're magnetic. The best example is O2. Now, O2 was being studied in the 1920s, 30s, 40s, and it was really trying to be understood, how is this thing magnetic? Liquid O2, for instance, and it's kind of hard to see in this picture a little bit, but there is a little bit of contrast here, that liquid O2 is being suspended between these two magnets here. If a material is non-magnetic, it literally just falls right through these magnets, but the oxygen is sticking around. However, in the Lewis structure, we can see that all of these electrons are paired up, and as we will see, magnetism requires at least one unpaired electron. So it was really confusing as to how something like O2 could be magnetic when the Lewis structure says everything's paired, and when valence bond theory also says everything's paired. So where is the unpaired electron? There are some other things as well, other observable phenomenon, such as particular molecular reactivities, or even spectroscopic results, like as we are going to be seeing more in the spring, some UV vis spectroscopic results, some infrared results, some Raman results that just don't line up with valence bond theory, that it alone cannot explain some of these observable phenomenon. So we needed another theory. We needed a patch, if you will, a 2.0, something that's going to work alongside valence bond theory, that's going to help explain where these phenomenon come from. So what is molecular orbital theory, and how does it differ from valence bond theory? Well, let's start by answering that first question. What's MO theory? According to molecular orbital theory, atomic orbitals, or AOs, merge into molecular orbitals, or MOs. This is different than valence bond theory because according to valence bond theory, atomic orbitals hybridize into new atomic orbitals, but they're still focused on the atom. Valence bond theory is focused on the atom. In molecular orbital theory, these atomic orbitals come together to make something entirely new, which encapsulates the entire molecule. Molecular orbitals allow then for the total rearrangement of electrons into brand new energy states according to what the molecule's stability is. For example, in one of the most simple rearrangements, according to molecular orbital theory, we can take one 1s orbital and a second 1s orbital, which signifies that in each of these individual atoms we have one little electron kind of hanging out. And as the two atomic orbitals come together, we, as a result, get one and a second molecular orbital. Now, these depictions of the molecular orbitals, what this language means, we're going to slowly break down as we go, so we will return to this. But from what we can see, there is one option for a molecular orbital upon this combination, according to this diagram, where the electrons now are said to be able to exist anywhere in between these two nuclei. This is akin to the orbital picture of like the diagram that I normally draw, where the electrons are kind of hovering back and forth. The electrons are allowed to be anywhere according to molecular orbital theory, holding the two nuclei together. Now in the second orbital, we can see that there is a pretty distinct node that exists between the two nuclei in the molecule here. This molecular orbital represents the two electrons being exclusively present on each of the two individual atomic centers. So we have to bring these two orbitals together to get a really good picture for the nature of electrons. On one extreme, the electrons being perfectly shared, in the other extreme, the electrons being not shared. All right, so let's start with some rules. Rules of molecular orbitals, because just like when we were first learning electron configurations for atoms, now we are going to be observing electron configurations for molecules. So there are a couple of extra rules we're going to have to pay attention to. First, two atomic orbitals must have similar energy levels in order to actually combine. What this means is that we can take two 1s orbitals and partner them together within an atom or within two atoms. We could take even something like a 1s and a 2s. I mean, energetically, these things are not too far away. Or even a 2s and a 2p, right? Same quantum number n. These three examples are pretty close in energy, so we would be able to combine them hypothetically to form some type of molecular orbital. What the actual shape of that orbital is would depend on the specific combination. However, we would not be able to combine something like a 1s and a 7s. These two orbitals are far too different in energy, right? The quantum number n equaling 1 versus 7 in the other is pretty different. Another example would be that of, let's say, the 2s and like the 5p. Again, far too different in shape, far too different in energy level. These would not be able to combine. So we have to make sure that our orbitals are similar in energy, which means that the electrons inside are also similar in energy. All right, rule number 2. Two atomic orbitals, when combined, will always result in one bonding MO and one anti-bonding MO, i.e., the number of resulting molecular orbitals always has to be equal to the number of atomic orbitals going into the picture. So if we have one atomic orbital and another atomic orbital, we're going to have to get two molecular orbitals on the other side. This is always going to be the case. Or if we combine three atomic orbitals, we're going to have to get three molecular orbitals on the other side. What this represents is a conservation of mass. We are going to need the same number of electrons out as what we put in. Now the labeling here, one bonding and one anti-bonding, also breaks down the types of molecular orbitals that we can have. So a bonding molecular orbital, just to go backwards, is signified when your electrons are able to hover between multiple atomic centers, when they are traveling between multiple nuclei. So this would be like the orbital illustrated here on the left. Because the electrons are able to hover back and forth, which signifies that the electrons are in some type of chemical bond, we would call this MO a bonding MO. And similarly, we would also need an anti-bonding MO. This is just a part of the rule. The orbital that is on the right is a depiction of an anti-bonding MO. And this is signified because the two electrons are not blending between the two atomic nuclei. They are staying separate. They represent that the two atoms are not interacting. They are not bonding. So for every combination, we are going to need a bonding and an anti-bonding. This is the equivalent of like the yin and the yang. We need some way for our molecular orbitals to describe the attraction between atomic centers, which is the bonding MO, as well as the repulsion between atomic centers, which is the anti-bonding MO. All right, so that's rule number 2. Rule number 3 states that all previous electron rules must also be followed. So this is the Aufbau principle, the Pauli exclusion principle, and Hund's rules. All of these must still be followed and obeyed. Just because we're working with molecular orbitals doesn't mean that the inherent behaviors and characteristics of electrons all just get thrown out the window. So we need to also adhere to these previous rules as well. So let's start looking at what different combinations we can have. How is it that the s orbitals come together, the p orbitals come together to make these real fancy looking molecular orbitals? Well, as we've seen already, 2 s orbitals will combine to form one bonding sigma orbital and one anti-bonding sigma star orbital. So this is the notation that we use. If there is a bonding orbital, which we've already seen illustrated, it is this first one here, assuming that there is a direct overlap, a direct blending, and the electrons are allowed to hover back and forth between our 2 atomic centers, we refer to this as a sigma MO. Sigma meaning that there is a single bond. There must also be the yang to the yin though, so we are also going to be working with this sigma star. What this represents, this star specifically, this is the notation for labeling an anti-bonding MO, meaning that we have no single bond. So as electrons begin to inhabit the molecular orbitals, we're going to have some electrons that are able to hover back and forth, stabilizing the molecule, and then there will be some electrons that will only hover around one atomic center, which destabilizes the molecule. Bonding, in other words, is low energy. Low energy equals stable. Anti-bonding is high energy, which is going to equal unstable. So all depending on the balance of the electrons in the bonding and the anti-bonding, you will either end up with a stable or an unstable bond, which means a stable or an unstable molecule. All right, so let's introduce what is known as a molecular orbital diagram. So far we've been seeing some pictures for atomic orbitals coming together to make molecular orbitals. We've introduced some new definitions, how we can label and talk about these different molecular orbitals. But outside of the context of this molecular orbital diagram, it doesn't really mean anything. We can think of this molecular orbital diagram almost like the electron configuration for the molecule. It helps us to figure out whether or not electrons are going to be in the bonding or the anti-bonding orbitals, and as a result, how stable the molecule is going to be. Now, the construction of the MO diagram ends up looking like a vertical energy diagram. And this illustrates, again, the stability or the instability of electrons in given molecular orbitals. So what we're going to do is pick out the most simple molecule that we can, literally just made of 2 protons and 2 electrons, and we're going to illustrate what this molecular orbital diagram looks like and how it tells us about the stability of this molecule. So how the diagrams come together. We are going to first start with one of the hydrogen's 1s orbitals. So this is the electron configuration of one of the hydrogens. We have a 1s orbital, so this is going to represent like our orbital box diagram, and there is 1 electron inside of it. Now on the other side, we're going to have another 1s orbital illustrated. This is going to be the other electron configuration of the second hydrogen. So it is also going to be contributing an electron as these two atoms come together. So really this is what we can think of, is that there's one 1s orbital over here on the left, one of our hydrogens, and it's going to be moving in towards our other 1s orbital here on the right, moving into the left. So they're going to meet in the middle. As the two 1s orbitals meet, according to molecular orbital theory, we are going to have a recombination into a bonding and an anti-bonding. Now the bonding orbital is stable, it is low in energy. So what this means is that in terms of energetic space, where on this y-axis we can think of energy as being low down below, high up on top, we're going to illustrate a new box, a new line, and this is where our sigma 1s is, meaning that we have a sigma bond, a sigma MO, between our two 1s's being combined. We will also have an anti-bonding, but because this is higher in energy, we are going to illustrate it up here, a sigma star 1s. So the organization here in the center symbolizes that the sigma 1s is lower in energy than the individual 1s orbitals where the electrons started from. The higher in energy sigma star means that this is higher in energy than the 1s orbitals that it was made from. So the 1s's are kind of like neutral, they're net zero. The sigma is down here, lower in energy than where it started, and the sigma star is up here, higher in energy than where the 1s's started. All right, we can also add the pictures for what these things look like, where the sigma 1s, again, was that kind of representation with the two nuclei in the middle and this kind of big balloon around them, symbolizing that the orbital now is encapsulating both of these nuclei. The electrons can exist wherever they want in here. And our sigma star is illustrated by the two nuclear centers having their own kind of balloons, but there's nothing in between. So we have these two kind of out of phase atomic or molecular orbitals. All right, so what do we do with these electrons then? Well, the electrons that started in the 1s orbital, or the individual 1s orbitals on these two hydrogens, are going to merge together in this new H2 molecular orbital diagram. And the way that we add electrons according to the Aufbau principle is from bottom up, right? We always go from low energy to high energy. So since we started with 1, 2 electrons separately, we are going to have to add 1, 2 electrons into the molecular orbital diagram in the center, coming from those two hydrogens. In other words, we're taking the 1s orbital electron from the left, funneling it down, and we're going to take the 1s orbital electron from the right and also funnel it down. So the two electrons that are in the center of this diagram are the same as the ones that were on the outside. They've just moved from the atomic orbitals on the left and the right into the molecular orbital here in the center. Okay, so this is the diagram then representing the combination of the two atomic orbitals, again on the far left and right, and the molecular orbital diagram itself is what is represented here, kind of outlining it in the center. So this represents in the center the electron configuration for the molecule. We can see we have 2 electrons in the bonding orbital and none up here in the anti-bonding orbital. What this means is that there is going to be a really nice stable sigma bond between the 2 hydrogens in H2. There is not going to be any anti-bonding character. The hydrogens will share their electrons evenly, which is going to really stabilize the molecule. One way that we can mathematically support that is by calculating the bond order that exists between the 2 atoms in a molecule according to molecular orbital theory. Now this is the same type of bonding order, I would say same as what we saw when discussing resonance. The equation explicitly may not be the same, but it's the same concept. We're looking at how many bonds are there between two different atoms in a more like Lewis structure kind of picture. So the bonding order calculation that we can do for molecular orbital theory, really this equation is for MO theory, is we're going to take 1/2 of all of the bonding electrons, and we will subtract out all of the anti-bonding electrons. This is going to tell us how strong the bond is between the two atoms that are coming together in this MO diagram. So let's return to our H2 picture and find what's the bonding order of H2. Well, our bonding order is going to be 1/2 of all of the bonding electrons. So let's go back to our diagram. According to our molecular orbital diagram, we can see we have 2 electrons here in the bonding MO. So we're going to take 1/2 of 2. We're going to subtract out the number of anti-bonding electrons we have. And the anti-bonding electrons, we can see we have none. So we're going to insert a 0 into our equation here. So 1/2 of 2 is just equal to 1. So there's a bonding order of 1 in between the two hydrogens. This matches our Lewis structure for hydrogen, H2, which we can illustrate like so. We can see that there is a single bond between the two hydrogens, which matches the bonding order calculation of 1 from the molecular orbital theory diagram. And this is really important. Just because the Lewis structure on its own doesn't give us all of this important like geometric or energetic information, it doesn't mean that the Lewis structures are super wrong. It just means that they're not the total picture. And we want to make sure that all of these theories that we are putting together work together. If there is one aspect of a theory that's kind of missing, it just means we don't have the total picture. If there's an aspect of a theory that disagrees with previous experimentally supported theories, it means that the part that is not meshing is wrong. So we can use these theories and kind of bounce them off of each other to get a really good picture altogether for what the molecule is, how it functions, what its shape is, and what its energy levels are. So far, we have worked with the 1s orbitals, combining them together, and using hydrogen as kind of a simple first step in understanding what molecular orbital theory is all about. So we're going to keep expanding on this conversation. So let's look at an example for how molecular orbital theory explains a molecule that doesn't exist. We're going to draw the MO diagram for He2, helium-2. This is something we know that doesn't exist. In fact, it's theoretically predicted that helium, even in, or like close, if not at absolute zero, will still exist in a liquid state. Like He2 is never going to exist. So let's calculate its bond order. Let's look at the diagram and use it to explain why this is just so impossible. Does this molecule exist according to MO theory? Spoilers, it doesn't. So let's see why. We are going to start with our 1s orbital on the left. Again, this is going to refer to the electron configuration of helium. We're always going to start with one of our atoms here on the left-hand side. In this case, it's going to be helium, as well as another atom here with its 1s orbital on the right-hand side, also equal to helium, also with its own electron configuration. Now, each individual helium has an electron configuration of 1s2. So we're going to put those 2 electrons into the individual 1s orbitals. As we combine these 1s orbitals together, we're going to end up with one nice low energy sigma orbital with a 1s subscript, meaning that the orbital came from the combination of these 2 1s atomic orbitals. And higher in energy, we are going to have the sigma star, the anti-bonding, the yan to the yin. And we're going to connect everything with dotted lines, which symbolizes where the molecular orbital itself came from. So in the center, we now have the MO diagram, the molecular orbital diagram, with this one really nice low-lying sigma 1s, in this one high-flying sigma star, 1s. Now we're going to add up all of the electrons present in the atoms individually, and then we're going to place them from bottom up in the molecular orbital diagram. So we can see across the first atom and the second atom, we have a total of 1, 2, 3, 4 electrons, and we're going to funnel all of those into the molecular orbital diagram. 1, 2, 3, 4. Now in the molecular orbital diagram, we can see that we have just created, which I'm boxing here. This is the MO diagram aspect. This is the new electron configuration. We have equal parts bonding and anti-bonding. If the number of bonding electrons equals the number of anti-bonding electrons, you have no bond. So for every electron in a bonding molecular orbital, you will have a bond present, but for every electron in an anti-bonding orbital, corresponding like so, we're going to see a slow deconstruction or destabilization of the bond. So if the 1s orbitals represent, in other words, like net zero, let's say this is 0 joules, hypothetically, and everything's relative here, so it's not like it's actually 0 joules, it's just 0 joules relatively. The 1s is going to be at a distance of like, let's say, -1 joules. It's, again, hypothetical relative distances. Well, the anti-bonding, being that yan, the equal yet opposite, is going to be equal to +1 joules, hypothetically speaking. Well, if you take -1 and add 1 to it, you end up back at 0. So what this means in terms of molecular orbital theory is that if you have equal parts bonding and anti-bonding, the atoms are actually more stable off on their own. The molecular orbitals are so unstable that these two heliums are like, you know what? No, we're not going to combine. I, as one atom, am going to stick with my own electrons, and you, as another atom, are going to stick with your electrons. So this is how we can make sense of He2 being something that just doesn't exist according to MO theory. MO theory describes the molecular orbital that results from the combination of helium's 1s orbitals as being so unstable that the heliums are like, nope, peace out, I'm just gonna hang up by myself. Atoms don't combine unless it's stable for them to do so. So if, in this case, we can see that there is a great instability, the atoms are just like, nope, no bond for me, thank you, I'll just be on my own merry way. Hi, yeah, this is also Dr. Billman in post. I can't believe I forgot to say this in the moment since we were just talking about bonding order, but also if you look at helium's molecular, or He2's molecular orbital diagram, you can see that there are 2 bonding electrons as well as 2 anti-bonding electrons. This means when you insert these values into the equation to calculate bonding order, you get 1/2 of 2 minus 2, which is equal to 0. What this means is that our bonding order is equal to 0, implying that there is no bond, right? There's not a first order bond, which is a single bond. There's not a second order bond, which is a double bond. It's a bonding order of 0, meaning that there is no bond. All right, sorry for interrupting. Keep going with the lecture. So far, we have been looking at combinations of s orbitals. A 1s orbital combining with another 1s orbital, and the same arguments could be made for like 2 s's, 3 s's. You bring them together, you get 1 bonding, 1 anti-bonding, single bond represented by a sigma MO. Well, p orbitals are a little bit more complicated in shape. And so when they start to come together, we're actually going to see something a little bit more complicated. So here we are now taking a step to increase in complexity. As 6 p orbitals combine, we end up with 3 different fundamental shapes. And of course, if we have 3 different fundamental bonding shapes, we will also end up with 3 corresponding anti-bonding shapes. So let's see where these come from. 6p orbitals combine to form 1 bonding sigma orbital, as well as 1 anti-bonding sigma star orbital. and the others combine to form 2 bonding pi orbitals, as well as 2 anti-bonding pi star orbitals. And wherever there's a pi, we know that this signifies double/triple bonds. So according to MO theory, we also have a description for where double bonds and triple bonds come from. So we are going to illustrate the molecular orbitals first as these p orbitals come together, and then we will see what their relative energy levels are. So the first important thing to recognize is that the p orbitals inherently on their own kind of occupy, like they may have the same shape, but they occupy different orientations in space. So if we say that our axes look like this, so if we have, let's see, what would this be? X, Y, and Z orientations in space, as Z orbitals come together versus X orbitals versus Y orbitals, we're going to see some different shapes as the result of the combination. So for instance, let's say we're looking at the Z direction first. Well, the PZ orbital on one atom is going to be arranged like so. It's just going to be laying down following this axis that I've illustrated up above. One of the orbitals will be of one phase, or one lobe of the orbitals will be of one phase, and the other lobe will be the other. So if we have another p orbital come into contact, again, same orientation in space, it's going to look like this. And again, the orientation here is going to matter. We want to make sure the lobes that are in the same phase are going to be touching. Well, here we can see there's going to be one kind of point of contact as these 2 orbitals blend together. And this will give us a molecular orbital that looks a little something like this. We're gonna have a little kind of like lobe over here, one really nice big, connecting lobe that's all going to be of the opposite phase, and then another little lobe kind of over here. So what this represents is the combination of these in-phase lobes of these 2 orbitals kind of generating something new, a really nice big balloon, again, that's going to encapsulate our nuclei. This is what represents the sigma subscript p molecular orbital. Just like with valence bond theory, one point of contact is going to represent a sigma bond. It's just that the picture here for the molecular orbital looks different than the picture according to valence bond theory. But the thing that they have in common is one point of contact. So this is our sigma MO for the combinations of p orbitals. If we observe, let's say, the orbitals along the y-axis, since that would be easier to draw up and down, we'll see one orbital here on the left corresponding to atom A. Again, one lobe will be out of phase with the other. And another orbital nearby, again, in phase with the first, is going to be able to come together and combine. It's just now, instead of having one point of contact, because we're in the same axis, we can see that these 2 orbitals are parallel, which would give us 1, 2 points of contact, as the red phases overlap and the white phases overlap. This is going to give us the illustration for a pi molecular orbital, where the upper half, let's see, is all going to be in phase together with the same kind of red coloring, or like colored inness, and the lower is all going to be the same, all that white kind of phase. So we have the colored in lobes combining and the white lobes, or the not colored in lobes, combining, and this is going to give us an illustration of a pi with the subscript of a p, MO. Now the molecular orbital along the x-axis is going to look very similar to the one that I've just drawn. It's just, instead of standing up, it's going to be laying down. But there are still going to be 2 points of contact in the atomic orbitals, which means as they come together, we're going to have the electron, or give the electrons, an ability to exist above the nuclei and below the nuclei, where the nuclei are going to be right here. So this is the description for our pi molecular orbital. Now the question is, which one of these are higher versus lower in energy, or are they equivalent? As these p orbitals come together, which is going to be the most stabilizing for the electrons in these 2 individual atoms as a bond begins to form? Well, as it turns out, sigma orbitals are lower in energy than pi orbitals. Sigma are lower than pi. And because the bonding and the anti-bonding are kind of that yin and yang, if the sigma bonding is lower in energy, the sigma star is going to have to be equal yet opposite, which makes it higher in energy than the pi star orbitals. And it's going to help to see this in more of an illustrated diagram form. So what we're going to do is illustrate the combination of oxygen's 2p orbitals specifically. So we could draw the molecular orbital diagram for the combination of all of the electrons inside of oxygen, but we are just going to focus on the 2p piece. And this is because, again, the atomic orbitals that are the most similar will blend together. So as we have two oxygens on the left and the right, the very, very low energy 1s orbitals are going to come together. The next in energy 2s orbitals will come together. And then above that are going to be the 2p. So that's what we're going to illustrate here on the right, just the combination of the 2p orbitals. So we're going to have one oxygen here on the left with its 1, 2, 3 different 2p orbitals. This is our oxygen on the left. And then our oxygen on the right will also have its 1, 2, 3 2p orbitals. Here's our oxygen. And in the middle, we're going to illustrate the combination for the 2p orbitals for O2. Now, according to what I just said, the sigma orbitals are going to be lower in energy than the pi. So we're going to arrange them like so. The sigma, the bonding, is going to be down below. This is the combination of our pz orbitals specifically. Next up, above that, are going to be the pi, specifically from the px, and the pi from the py. Right, so these are the three different bonding molecular orbitals that can result, that are all going to be lower in energy than where they started. The anti-bonding are going to be across this threshold, equal yet opposite in the above, or the anti-bonding kind of area, the repulsive or unstable area. We're gonna have a pi star for the px, and a pi star for the py. This is an x. And then last but not least, the highest in energy is going to be the sigma star for the pz. So again, we want to make sure that if our sigma, our bonding, is kind of like nice, even, stable down here, the anti-bonding is going to have to be like equally above this central threshold where the 2p orbitals started from. So that's how we can really conclude that the pi star is going to be below the sigma star. Why the sigma star is going to have to be the most repulsive, it's because the sigma bonding is the most attractive. All right, so now that we have the diagram illustrated in the middle for the combinations of our 2p orbitals, we can add in our electrons. So oxygen's electron configuration is going to be core of helium, 2s2, 2p4. So this 2p4 tells us that there must be 1, 2, 3, 4 electrons here with our oxygen on the left, and 1, 2, 3, 4 with our oxygen on the right. This gives us a total of 8 electrons that are going to get funneled into the molecular orbital. So we're going to start from the bottom. 1, 2, 3, 4, 5, 6. And here also we must remember Hund's rule. Since there are 2 electrons left, we're going to have to place them in the anti-bonding, and the most proper orientation is going to be to spread them out. We want to fill each orbital individually before we start pairing them. So in the center here, again, we can see our combined molecular orbital diagram for O2, specifically the combination for our 2p orbitals. We end up with a nice combination of bonding down below, as well as a little bit of anti-bonding characteristic. Now, this doesn't completely break all of the bonds between the 2 oxygen atoms, but what it does mean is that O2 is going to be a little unstable. In fact, this is molecular orbital's description for why O2 is so reactive. Right, oxygen in the atmosphere will freely combine with things like iron to cause rust. This is because O2 is pretty reactive. It's reactive enough to just go out and try and combine with things all on its own. And we can attribute this, according to molecular orbital theory, to these Anti-bonding electrons, they are going to be so reactive, they're going to want to get off of this molecule, they're going to want to go react somewhere else. So in conclusion, this is the combination for our p orbitals in a molecular orbital diagram as we bring these atoms together. All right, so let's look at the big picture then. As I stated previously, just on that last example, we could draw the molecular orbital diagram for all of the electrons present in some given atom, or some given molecule, excuse me, from the combination of atoms. The most useful orbitals to look at are going to be the combinations of the valence electrons. So that's going to be what we do for this N2 here. This is what we call a homonuclear molecular orbital diagram. This is a diagram that corresponds to a diatomic molecule that is comprised of these same elements. So, for example, we've already drawn H2 and O2. Now we're drawing N2. All of these are homonuclear MO diagrams. But in order to draw nitrogen's homonuclear MO diagram the most correctly, we also have to acknowledge one last special rule. This special rule states that if the atomic number of the elements in your diagram are equal then or less than or equal to 7, we must invert the energy levels of the bonding sigma and the bonding pi. Now, why this happens is a conversation that we save for like a more advanced class, specifically inorganic chemistry or Chem 406 at the college that I work at. The reason why is we need a little bit more information to really understand why this happens, but here at the general chemistry level, we're just gonna add it as a special rule and state that this does happen. So let's draw the MO diagram, like the entire valence shell MO diagram for N2, just to see what this is gonna look like. So one of our N2s is going to be on the left, and instead of illustrating the electron configuration horizontally, we're gonna do it vertically. Again, from low energy down below to high energy up above. So the valence electron configuration for any one of our nitrogens, let's see, is going to be a core of helium, 2s2, 2p3. And again, we're focusing on valence, so we're going to add a 2s electron down below, and we're gonna have 1, 2, 3, 2p orbitals up above. Same thing on the right-hand side, 2s orbital, and 1, 2, 3, 2p orbitals up above. Now let's place the electrons now. Why not? There's no reason why we always wait to the end. It's just kind of been convenience so far. So let's add the 1, 2 electrons in our 2s, 1, 2, 3 electrons in the 2p on the left-hand side, and we'll do it for the right as well. Now here we are going to start combining our atomic orbitals together, nitrogen on the left, nitrogen on the right, N2 in the middle. First, we're going to have a sigma from the 2s, this is our bonding MO, as well as a sigma star, 2s right here. So in our special rule, we don't have to invert anything here because when we combine 2s orbitals together, there is no pi. So there's no inversion that needs to happen here. We're going to add our 1, 2, 3, 4 electrons into this combination, 1, 2, 3, 4. Now that we move on to the p orbitals, here's where the special rule is going to come into play. Since nitrogen has an atomic number of 7, we are going to have to invert the sigma bonding MO and the pi bonding MO. What this means is that we're going to end up with the pi's down below and the sigma up above, only in the bonding case. So here's our pi, here's our pi, here's our sigma, specifically for the px, py, and pz. So the bonding will be inverted, the anti-bonding will not be inverted. So it will still be the pi star for the px, the pi star for the py that comes next, and last but not least will be the sigma star for the pz. And then we can connect all of our dots, each of these sigmas and pi's coming from the 2p orbitals of either of the atomic orbitals on the left and the right. And then here we go. Here is what our molecular orbital diagram is going to look like for N2. Last but not least, we have to add the electrons, all 6 of these electrons from the individual atoms on the 2p side. 1, 2, 3, 4, 5, and 6. So now in the center, we have our molecular orbital diagram. We can see that there are 2 s, sigma, and sigma star, kind of canceling each other out. But up on top, we can see that there are 3 nice sets of bonding MOs, the PZ, the PX, and the PY coming together to make sigmas and pi's. Now that we have returned the conversation to oxygen, and we have learned how to illustrate these molecular orbital diagrams, let's start linking them to some of these, again, physical kind of observable phenomenons, things like magnetism. Now, there are 2 definitions that we need to lay out. The first corresponds to not magnetic, and the second corresponds to yes, magnetic. So the first, diamagnetic, by definition, states that this is a substance with no unpaired electrons. Everything is paired, hence the di in diamagnetic, right? Everything's partnered together. Things that have no unpaired electrons are weakly repelled by a magnetic field. Again, what this means observationally is that it's not magnetic. This is the equivalent of like trying to take a magnet, like a fridge magnet, and put it on like an aluminum surface. It just doesn't stick. This is because aluminum does not have any unpaired electrons. It is not going to actually work as a magnet or as a magnetic substance. Paramagnetic, on the other hand, this is a substance that, yes, does have unpaired electrons, which means that it does get attracted to a magnetic field. Yes, it is magnetic. Para means 1. That's really 1 there, just to make my handwriting really clear. So since there is an unpaired electron, we have 1 electron that does not have a partner, hence the term paramagnetic. So it turns out, observationally, that you need an unpaired electron in order to be magnetic. And the reason why is this 1 unpaired electron is just seeking a partner. It's seeking stability in any case, in any way. And it just so happens that by orienting itself with a magnetic field, aka an electric field, it can gain a little bit of stability. So it's more stable for an unpaired electron to align with a magnetic field than it is to not. Hence why then it ends up getting stuck to an object that is magnetic, because it's more stable for the electron that way. All right, so the paramagnetic substances have unpaired electrons. And as previously stated, when we first started this whole conversation, we were trying to figure out how it was that oxygen ended up being magnetic when other things weren't, particularly because according to its Lewis structure, everything was paired together. So what we're going to do is go back and observe the diagrams for O2 and N2 and determine which is paramagnetic and which is diamagnetic. Now, because I've also scribbled all over the previous molecular orbital diagrams, what I'm going to do is just redraw them here for clarity's sake. So 3, 2, 1. There. I have illustrated all of the molecular orbital diagrams, or the 2 that we were going to be looking at, for O2 here on the left and N2 here on the right. So we can observe the molecular orbital diagrams, and whichever of the central portions of the MO diagrams have unpaired electrons, this means that we're working with something that's paramagnetic. And if we observe an MO diagram that has only paired electrons, we can predict that this substance would be diamagnetic. Well, if we start with O2, here we can see there are 2 unpaired electrons, which means that we would, according to this molecular orbital diagram, predict that this is going to be a paramagnetic substance. We predict, according to molecular orbital theory, that oxygen will be magnetic, which is observationally true. Once molecular orbital theory back in the 1930s, 1940s demonstrated that it could predict the magnetism of oxygen. This is really when MO theory started to become really popularized and kind of equal in perspective to valence bond theory. Other substances like N2, we can see MO theory also works to predict what their behaviors are going to be. N2 is not observed to be magnetic. It is not attracted by magnetic fields. It just kind of slides right on through, doesn't really care. Here in the molecular orbital diagram, we can see that there are no unpaired electrons. This means that our N2 is going to be diamagnetic. It is going to have only paired electrons inside of the molecular orbital diagram, and the pairings of these electrons causes each of the individual partnerships to be totally stable. The material doesn't need to align itself, electronically speaking, with the magnetic field in order to become stabilized. It's fine just off on its own. So because MO theory can predict when substances are magnetic and when they are not magnetic with great accuracy, MO theory is a really awesome theory to be able to use to predict certain energetic phenomenon for materials like magnetism. All right, so is that it when it comes to MO diagrams? Nope. There's one more thing that we are going to talk about today, and it's how we approach drawing heteronuclear MO diagrams. Now, these are MO diagrams that correspond to a diatomic molecule that is comprised of two different elements. And here we have another special rule. This is a special rule for heteronuclear MO diagrams. Since the two atoms are different, what this last rule acknowledges is that different atoms have different energies. And according to this rule, the element that has the greater electronegativity is going to end up being lower in energy. So for instance, if we wish to draw the molecular orbital diagram for NO, in fact, let's just focus on the combination of the two P's in NO just to save ourselves a little bit of time. We can, to start, we're going to have to, just like before, draw the atomic orbital electron configuration. So our 2p for nitrogen is going to be here. But because oxygen is more electronegative, its atomic orbitals are going to be lower in energy. They're going to be down here, oxygen. So this discrepancy in energy is going to have some pretty strong implications. So let's illustrate what the molecular orbital diagram here is going to look like, and then once it's drawn, we can kind of tie together these implications. Now, because nitrogen, again, is number 7, this means that as we draw the molecular orbital diagram, we're going to have to follow the previous special rule that we learned as well, being that the sigma and the pi's are going to be inverted, and that's totally okay. The anti-bondings, again, will not be inverted, so pi star will be next, and then sigma star will be above that. And I can draw all of the dotted lines, kind of connecting everything like so. Dotted line, and dotted line. All right, and last but not least, we're gonna have to add in the electrons. Then we can observe bonding order, para versus diamagnetism, as well as this last kind of characteristic that we can observe. All right, so nitrogen has 1, 2, 3 different 2p electrons. Oxygen has 1, 2, 3, 4 different 2p electrons. This gives us a total of 7 that we are going to have to add into the molecular orbital diagram in the center for NO, or nitrogen monoxide. 1, 2, 3, 4, 5, 6, 7. So we have 1/7 electron up here in the anti-bonding. So now that every electron is placed, let's start drawing some conclusions, making some predictions about the nature of nitrogen monoxide. First, let's start with the bonding order. bonding order is going to be equal to 1/2 of all of the bonding electrons, which we can see here are a total of 6, as well as the anti-bonding electrons up on top, -1. So our bonding order is going to be 1/2 of 6 minus 1, which is 5, which is equal to 2.5. So this is a really interesting case here, where the implication of this bonding order is that we are going to have a possible resonance structure between something that is triply bonded and something that is doubly bonded. So the electrons are going to be pretty loose and free-flowing over this structure in order to give nitrogen monoxide some stability. It's especially going to need that stability because we have this one anti-bonding electron. Now, this one anti-bonding electron is unpaired, meaning that we would predict that nitrogen monoxide is going to be paramagnetic. So it should be magnetic. We would see it being attracted to magnets, held to magnets, etc. In addition, this one unpaired electron is going to, especially because it's in the anti-bonding orbitals, is going to make nitrogen monoxide very reactive. Now, this reactivity we would already predict because nitrogen monoxide is a free radical. We've already seen what the Lewis structure for this molecule looks like. And so because the Lewis structure had an unpaired electron in it, we had already predicted it'd be reactive. Here we can double down on that. Molecular orbital theory also agrees with this molecule being pretty reactive. All right, and the last characteristic that we can talk about then is because the nitrogen and the oxygen originally had such different energy levels, we can see that the anti-bonding molecular orbitals are similar in energy to nitrogen, and the bonding molecular orbitals are similar in energy to the oxygen. What this tells us is that the nitrogen is the unstable atom in the molecule, right? This reactivity from the unpaired electron, the paramagnetism, is going to be mostly focused on the nitrogen. The oxygen is going to be the stabilizing atom in the molecule. Like when nitrogen combines with the oxygen, we can see that the bonding orbitals become way more stable compared to nitrogen's starting place, and this is because of the oxygen. The oxygen is going to help stabilize the nitrogen, even though it's the unstable species, the more reactive species. The oxygen is what's going to help tie the molecule together. All right, now that we have learned all that we can learn about homo and heteronuclear diatomic molecular orbital diagrams, let's try drawing one just from scratch, right? Just all over again. One last example. You know, this last example is set apart because the molecule that we're going to be drawing, oxygen monofluoride, also has a negative charge. This tells us, just because we're going into this problem, that we can also draw molecular orbital diagrams for diatomic polyatomic ions. So things that have negative and positive charges. So that's what I want you guys to try your hand at. So please, if you have not yet, pause the video, attempt drawing the molecular orbital diagram for OF- on your own. And I will say also, just for some good practice, include the valence 2s and 2p. Include both the inner and the outer valence subshells. Use your molecular orbital then to determine whether or not this molecule is going to be para or diamagnetic. All right, everyone, let's come together. Let's illustrate this molecular orbital diagram for OF-, and let's include this extra negative charge in here as well somewhere. All right, so step one, let's draw the atomic orbitals on the left and the right-hand side. Oxygen I'm going to put on the left just because it's listed on the left in the molecule's formula, like that's the only reason. So oxygen, I am going to draw its 2s orbital, let's say here, and it's 3 different 2p orbitals right here. And since this is oxygen, we're going to add 1, 2, 3, 4, 5, 6 valence electrons into the combination of the 2s and the 2p. Now fluorine, because it is more electronegative, when we draw its atomic orbitals, we're going to have to draw them a little bit lower. So I'm going to draw fluorine's 2s orbital down here, and fluorine's 2p orbitals 1, 2, 3 right here, 2p. Exactly where the placement is, like exactly how much lower you have to draw the 2s and the 2p, I'm gonna say at the general chemistry level, you don't have to worry about it. We end up seeing more specific energy levels in organic chemistry, P-Chem, actually inorganic, like the non-organic chemistry. So we'll be seeing more of the specific energy levels a little bit later. For now, just know that it should be either higher if you're working with a less electronegative element, lower if it's more electronegative. All right, so let's place in the 1, 2, 3, 4, 5, 6, 7 valence electrons for fluorine. And before we forget, there is also an extra negative charge here. So where do we put the negative? Customarily, is that even a word? By custom, we place the extra electron on the more electronegative atom. So En for electronegative. So this means that because the OF minus has an extra electron, we're gonna place that extra electron right here on the fluorine. Conversely, if when working with a polyatomic ion that has a positive charge, positive charges take electrons away from the less electronegative element. So for instance, if this was OF plus, we would have taken the electron away from the oxygen. All right, so now that we have the atomic orbitals illustrated, let's just combine these together. The two S's will give us a sigma as well as a sigma star. We'll connect the dots here. We're going to place all 1, 2, 3, 4 electrons into the sigma and sigma star. And as the two p orbitals come together, we can see that neither of these atoms is less than or equal to number 7 on the periodic table. So for this reason, we don't have to do any weird inversions. The sigma is going to be the lowest. Then our pi's above that, pi star above that, and sigma star last but not least. Let's see, so I'm gonna roughly and kind of loosely connect the dots. I don't want to like cluster up everything too much or like make it too confusing to look at. So now that we have the 2p combination illustrated, we're going to take our 4 electrons from oxygen, our 6 electrons from fluorine, that gives us a total of 10 electrons, and we're just going to place them into the diagram here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So now we have our molecular orbital diagram illustrated here in the center for OF minus. And from it, we can either calculate the bonding order if we want, compare it to the Lewis structure if we want, make some conclusions about the reactivity if we want. But in this specific example problem, we are only asked to determine whether or not this thing is going to be para or diamagnetic. So we can observe, are there any unpaired electrons here? We can see that there are no unpaired electrons, which means diamagnetic. Dia again, implying that all of our electrons have pairs. All right, and that is it for drawing our Lewis structure, evaluating its para versus diamagnetism. And so in conclusion, since we have spent a fair amount of time observing valence bond theory and molecular orbital theory, let's just draw some last conclusions, some final conclusions. Valence bond theory, what we talked about in our previous lecture, focuses on the atoms inside of the molecule. It is very atom focused. It also explains the arrangements of the electrons on that per atom basis. So even the hybridized orbitals are on a per atom basis. But when you put these together, we can get a really good explanation for the physical geometry of the molecules, better than had we not developed valence bond theory in the first place. Molecular orbital theory focuses on the molecule as a unit, not the individual atoms and not the individual bonds. Molecular orbital theory is also used to explain the electronic structure of molecules as well as specific phenomenon such as magnetism. All right, so we need both valence bond theory and molecular orbital theory in combination to be able to explain the physical and chemical characteristics of atoms in molecules. And with that, we conclude Chapter 7. So here I have a couple of example problems for everyone to work through pertaining to Chapter 7. And with that, we're just going to call it a day. So if you have any homework, please double check and do your homework. But until next time, class is dismissed.